Okay, so we continue on the variance estimation for under the systematic sampling. The fourth one I like to introduce is called the differences method. So using the differences method, it can help us to estimate the variance of the yi. So suppose y bar is a non-zero number, then we can compare each of the yi data that we collected. Let's call it dij. And to indicate the difference between two of the data that we collected. In some cases, we can look at the successive difference or we can look at the collapsed difference. If we consider successive differences, so di is equals to the difference between the yi plus 1 minus the yi data. And then we know that the expected value of yi is equal to the expected value of yi plus 1 because they are all from the same set of populations. So in this case, if we take an expected value of the differences is indeed equal to 0. And then we want to look at the variance of this di or dij, okay? So look at the differences of two independent variables. Differences is indeed adding up the variance of yi plus variance of yj. And we know that variance of yi is no difference from the variance of yj because it's actually adding up two of the sy square, because each of them would illustrate the variance of the sy square. So adding them up, if yi and yj are independent, then we are having 2 sy square. So if that's the case, we can make up nd numbers of those differences if we're looking at the successive differences. So if this is the case, we can now look at the sd square is indeed equals to the summation of di square, which is the successive differences, taking a square divided by nd. And we have nd instead of the nd minus 1 because we are looking at the true means of the expected value of the di. So if this equations substitute into to replace the sy square in the variance estimate for the equations, and then we can substitute that, replace that sy square by sd square, and then we can use the estimated variance under the differences is indeed equal to the finite population correction factor multiplied to, instead of sy square over n, now we have sd square over 2n. Okay, so I just read it out explicitly for you to look at the equations. So first of all, the difference dij is equals to yi minus yj, and the expected value of this two is equal, and then expected value of the differences is indeed equal to 0. Then we look at the sd square is equals to the variance of dij, and dij is the difference between the two independent variables. So adding them up is actually equals to 2 sy square. So we try to relate sd square divided by 2 is equals to sy square. Okay, and there are nd differences between all numbers of the successive differences. So if that's the case, we need to divide sd square is defined as the summation of di square. So look at the differences, taking square and sum them up, divided by number of the successive differences, nd. So replace the sy square in the estimated variance formula by sd square divided by 2. Then we can find this equation, the estimated variance of y bar using a differences method is equals to the finite population correction factor multiplied to sd square, which is summation of di square over nd, and divided by 2n. Okay. So a couple of comments. First of all, the differences di can either be yi minus yj, any difference between the two variables that we collected from the sample, or as long as they do not equal to each other, or they could divide as the successive difference, so the next number minus the previous number. And secondly, that we mentioned, we divided by nd instead of nd minus 1 because they are the true mean of the di's instead of the estimated. Okay, so there are several ways of forming the differences. So we just mentioned that either we can use a collapsed estimator or successive estimator. Okay, using the collapsed stratum estimator, then the SD square will be defined as the difference between any two yi data, and take a square given their difference, and then the third and the fourth, and the fifth and sixth. So there's no overlapping of all the data. So in other words, we actually divide the entire set of the data into m pairs. So that becomes y1, y2, y3, y4 in one pair, 5, 6 in one pair, etc. Okay, so in this case, we're looking at the differences and taking square divided by m, and to find the SD collapsed estimator square, and then substitute into the estimated variance formula to find 5.10. Successive difference estimator is indeed looking at the differences between any successive data we collected for yi, j plus 1 to the previous data differences. So in this case, we are looking at the difference between the first data and the second data, and then the second to the third, third to the fourth. So they are an overlapping of the data because we're looking at the successive differences. In this case, we're not divided by the total number to n pairs, but indeed we would be having n minus 1 of the differences. So we need to divide this summation of the square of the differences by n minus 1 instead of m for the successive differences. Okay, so again, substitute this into the same formula. We can estimate the variance of y bar using differences method. Okay, so just to rewind a little bit. So under systematic sampling, we would have 4 methods of estimating the variance. First would be assume the population is randomly distributed. So we are as good use the simple random sampling estimator. Secondly, we can use repeated systematic sample. So from one systematic sample, we divide them into repeated systematic sample. And then we can estimate the variance of the repeated systematic sampling. And then thirdly would be a simple case of the repeated simple sample would be half size repeated systematic sampling. And then fourthly would be the differences method. And within differences method, we can further expand it into collapsed differences or successive differences. Okay, so let's look at example 5.5. A reporter wants to estimate the average January precipitation across US, and he only has time to call 8 stations. From an alphabetical listing of the 88 weather stations across the US, he obtained 8 data points. So he collected the data in a systematic way, 1 in 11th of the station, and then he collect 8 data points. Okay, so here are the data for the numbers of the precipitations: 0.5, 1.8, 1.9. Estimate the average of the rainfall based on those 8 numbers. So first of all, we can look at the average of the 8 numbers, and we find that's equals to 1.98. Or assuming that we go back to the first estimation of the variance, assuming there's no trend out of those data or across alphabetical orders of the stations, there's no trend of the rainfall. They're quite randomly distributed. So we can use our SRS estimator of the variance equations to estimate the variance. Okay, so that equals to final population correction factor multiply to SY squared divided by 8. So the estimated variance is about 0.196. And then we doubt that maybe that could have a small cyclical trend of the data across US or across the data that we collect in that alphabetical orders. So we can try to use the differences method to see if the variance obtained from the differences method would be substantially reduced. So that means using SRS is actually overestimating the true variance. So we apply the differences method. Okay, so let's put all the data in this way, and then we can have the summation of the 8 data divided by 8. So again, we have the average 1.98. Look at the difference, di. So we are using successive difference in this case. So look at the difference 1.8 to 0.5, which is 1.3. 1.9 minus 1.8 is 0.1, etc., etc. Okay, and then we are interested in the di square and the summation of the di square because of the SD square using successive difference is indeed equals to the summation of di square divided by n minus 1. We're using successive differences, so the number of data we collected is n minus 1. Okay, so which is 7. So we find SD squared equals to 3.107. Substitute that into the estimated variance formula. Instead of using sy squared over n, we are using SD squared over 2n. So the estimated variance is about 0.1765. So compare this differences method's estimated variance is very close to the SRS estimator. So we can say that we do not see a substantial reduction in the variance estimate. So we can say that it worked well if we use a SRS estimator as well as the differences, even though we doubt or we thought there would be a cyclical data point. Okay. So note that we should use variance estimate based on the successive differences whenever we suspect the population elements are not randomly ordered. And then we can see that if we are quite sure if the population is randomly ordered, then we can use an SRS estimate. If not, then we would suspect there would be an increasing trend that we rather not use the SRS estimator. So let's look at example 5.6, or I should use I have the 4 data point collected in a systematic way. Okay, so if I use the SRS estimator, I find this is my estimated variance. But indeed, if I use a repeated systematic sampling, let's say the half sample, I can substantially reduce the variance estimate. Or even if I use a collapse differences or successive differences method, I also find a substantial reduction in the estimated variance. So we find that actually the data itself would have an increasing trend. So the variance approximation from the SRS will overestimate the true variance if there exists an increasing trend for the data itself.